Hello, everybody. Welcome back to the second installment of our micro lectures in statistics. Today, we're going to continue on with where we left off last time and sort of understanding what statistics is as a field and what it does and how it does it. Okay, so a quick recap, of course, is that statistics uses math and principles of probability to look for patterns inside of information, a set of information, and then to establish whether those patterns are useful or make any sense, for example. Okay, so just as one example, we could say that let's imagine we do some kind of research project and we find that caffeine consumption appears to be related to alertness. We could, of course, get into the weeds about how we're measuring alertness, how how well controlled our study is. All of that kind of stuff is fine. But for our purposes, let's just imagine that we find an association between caffeine consumption and subjective levels of alertness. Now, the problem is statistics can't tell us whether caffeine actually causes the alertness, okay? And anybody who tells you differently is lying to you. Statistics cannot tell us whether for sure we know with 100% certainty that caffeine causes alertness. However, what statistics can do is tell us the likelihood that it does cause alertness. Now, maybe we can get to 99% likelihood or even 99.99% likelihood. That's very unlikely in real life, but that we could find a probability that high. But that's what we're dealing with, is the likelihood that it does occur and the likelihood of how well we know how much it does that, for example, which is getting a little bit ahead of ourselves. So this taps into something called Bayesian statistics, which is a very rich thing we could talk about. I could spend a couple hours probably talking about that. Bayesian statistics is named after a very famous statistician who was named Bayes. I won't get into all of that, but you can read about him later. Bayesian statistics essentially states that I can't say yes or no. I can't say that caffeine affects alertness. What I can do, however, is say there appears to be, for example, an 80% likelihood that caffeine affects alertness. Okay. Now, to apply that in our everyday life, let's imagine that I say, gosh, I'm going to get this raise at work. I'm going to get this raise, or I'm certain I'm going to get this raise. Well, you can't be certain, but what you could do is put a probability to that, right? According to Bayes' idea. I'm 45% likely I'm 45% sure I'm going to get this raise at work, right? I'm 70% sure I'm going to get this raise at work. And then what's the rest of that is maybe uncertainty or something like that, right? And so that's the kind of thing that we're working with throughout all of statistics in the modern day, essentially. Okay, so it's difficult to sort of convert your thinking into that idea, but instead of saying yes, this is going to occur tomorrow, you think of it in terms of likelihoods and probabilities. This is something we'll revisit throughout all of these. Okay, now of course one issue, the sort of natural issue here, is that if I say that there's an 80% likelihood that something is true or correct, for example, that these two things are associated, what that also means is there's a 20% likelihood that I'm wrong about that, okay? And that's something very important in statistics that we need to focus on here, because that error is something very important that we try to be aware of and control for. So let's now talk about the mistakes that can occur from a statistical test. So in any statistical test, there are four possible outcomes. So first of all, your test could say that you do find two things are associated. We'll say two variables, right? You have two variables that are associated, or the test could say you have two variables that are not associated, they don't appear to be associated. And then that finding could be right or wrong in reality, right? Because again, if I have if my data tell me there's an 80% likelihood this is true, that means there's a 20% likelihood it's not true, essentially. And so I can go with what the test says with the risk of being wrong. And as statisticians or researchers, we do our best to minimize these kinds of risks, okay? So in a perfect world, what we have is that we get it correct, right? So for example, let's say that I do my study and I find that I find evidence to suggest that caffeine is related to alertness. So what I say is that they are related, and maybe the reality is that they are related. So if that's true, if I get it right, and caffeine actually is related to alertness in reality, which of course, nobody really can say for sure, although we're pretty confident in that, of course, at this point. Then I got it right. In other terms, I might say something like, I don't know, are vaccines related to autism? Do vaccines cause autism? And if I do a very careful research study and I find, oh, I don't find evidence that they are related, and in reality they're also not related, then I get that correct. Okay, so that's good. That's what we want. We want to make the correct call. And of course, in many cases, we don't actually know what the reality is, but we gather evidence to sort of suggest and support what the reality probably is. Now let's look at the mistakes. Okay, so there are two possible mistakes then. For example, I might say that they are not related. In this case, I say they're not related, but in reality they are related, okay? Something like that. Or I could say they're not related. I'm sorry, I could say they are related, and in reality they're not related, okay? So those are the problems is when it falls into that 20%, for example, where I I followed the evidence and the evidence was actually wrong. There was some fault in my research. Okay. So these are called the type 1 and type 2 errors, is when you made a mistake. It's a false positive or a false negative. So I'll talk about that really quickly. If you get a positive result, that means that you said that there was a relationship. That's a positive result. A true positive result means you said there was a relationship and there really is. A false positive relationship is when you said there was a relationship, but in reality there isn't. Okay, so let's dive into these just a little bit more. Okay, the mistake where you say there is a relationship between two variables, but there actually isn't, is called a type 1 error. That is a false positive, right? I concluded that they are related, but in reality they're not related. And a real quick point here is that this isn't necessarily on purpose. It's not that I'm lying to the public. It's that the evidence just didn't line up with the reality. I do not have a crystal ball that tells me the true nature of the universe. I do not have a direct connection with a deity, for example, that tells me exactly the way that all things work in the world. Okay, and so I'm left simply with my observations, and they're messy sometimes. There are sometimes things that get in the way, or as we'll see, Murphy's Law very much applies to statistics, where sometimes things just occur. If they can occur, they will occur, maybe just by accident. Okay, anyway, so that is called a type 1 error, when you say that these two things are related, and in reality they're not. So for example, one thing could be if I say that vaccines cause autism, and this claim has been made, but it turns out that in reality they don't, and nobody knows for sure. But there have been a lot of very high quality research projects done on this, and the general consensus now is that there is no clear link between vaccinations and autism. Now, there was a nice theory that sort of lined them up, and it was perfectly worth investigating, and yet the research now, all evidence points to no, vaccinations do not cause autism, certainly not in their current form. Okay, so again, it's not usually that somebody's lying, it's just that they probably made some mistake, right? We can't be absolutely certain using statistics and research methods until we do get that crystal ball, for example. Okay, the other type of error is called a type 2 error. This is a false negative error. This is when your research tells you, hey, the evidence doesn't find a relationship between the things that you're measuring, and you get that wrong. You're actually wrong by saying that. Your evidence is out of whack. Your evidence doesn't line up with reality, which is, of course, very unfortunate. Okay? So, for example, if I tell you that, yeah, asbestos seems perfectly safe. It seems like a very cheap, sturdy building material. Let's put it in all of our stuff. Let's put it in our insulation. Let's build tile out of it, and all that kind of thing. And I don't think it causes any health problems. In reality, of course, now we know that it does cause massive health problems. It's very dangerous, especially when it's in the air and you're breathing it. And so this would be a real big problem if I falsely conclude that there is no relationship when in reality there is a relationship. That is a false negative. The negative is I said there's no relationship, and it is false. There actually is. Once again, it's not that I'm lying necessarily. Maybe I am, but it's usually just that my research methods weren't rigorous enough, for example. My criteria, my threshold for actually saying that this was a negative result was too low, for example, or multiple other factors, which we'll get to throughout all of this. Okay, so that's a type 2 error, or a false negative error. Okay, so this is a really big problem in statistics, and what statisticians and researchers try to do is minimize both errors, both likelihoods of those errors, the type 1 and type 2 errors. It's always a challenging thing to do, though, and in fact, it's very difficult to get a nice balance where you have minimal risk of both. In fact, usually you have to trade off some risk of one of those for reducing the risk in the other. So it's very challenging to do that. So for example, if I say, okay, well, I really don't want to commit a false positive, so therefore I'm going to have a very high threshold before I say that these two things are related. What that then does is forces my risk of a type 2 error to increase, because now I'm saying, therefore I'm more likely to say that these things aren't related. And they might be, right? And so if I increase my, or if I'll say lower my risk of a type 1 error, I sort of necessarily increase my risk of a type 2 error. And so there's never a way to reduce both of these to zero, unless you have a crystal ball. By the way, let me know if you do, and I would like to buy that from you. Okay, so this is a very difficult problem that continues throughout. Just as a basic rule, especially in social sciences, we typically do not allow more than a 5% likelihood of a type 1 error. Okay, and how we do that is very clever, and we'll talk about that later. We typically, for the type 2 error, we don't usually go above about 20%, but again, this will vary based on lots of things in the actual research project, and especially the variables that you're working with. So that's sort of a guideline, but take it with a grain of salt, of course. Okay, so what this means is that researchers often are sort of by default conservative in what they're doing. They're very cautious because of these errors. These errors keep them awake at night. They make them very nervous, and so a good researcher is very cautious about reaching any kind of conclusions unless the evidence really seems to point towards that and support that. And then we're sort of left with cautiously saying the evidence leads me to this conclusion. Okay, so a quick recap is statistics do not tell us the absolute truth of one thing over the other. What they do is tell us how likely one thing is to be correct versus incorrect. And so you need to very much keep that in mind. And so we go with those likelihoods, right? Yes. All right, and so we need to be very cautious about these type 1 and type 2 errors. You need to start doing this in your life as well, in your own relationships. For example, if you conclude this person is the right person to date, maybe they're not. What is your threshold for that type 1 versus type 2 error in relationships, for example? Anyway, but we'll use these in all sorts of other interesting situations for statistics. That's it for now, but I'll see you next time.